So actually on Saturday we stopped at spin quantum number. So we told you that we have 4 types of quantum number. On Saturday we looked at quantum number. I will say we have 4 types of quantum number. We have principal, we have azimuthal. Another name for azimuthal quantum number is subsidiary quantum number or angular momentum quantum number. We have magnetic quantum number. And then we have spin quantum number. Each of these 4 quantum numbers have their symbols. For the principal quantum number, N representing the number of shells. N representing the number of what? Shells. Azimuthal is L. Magnetic is ML. Spin is MS. Class, we recognize their symbol first. The principal quantum number is the shell level class. It tells us to know the number of shells. The shell energy level. The principal quantum number is at the shell energy level. But as azimuthal quantum number helps us to know, go deeper than the shells into the orbitals. And we say orbitals are called subshells, are called sub. Then the magnetic quantum number helps us to go even more deeper into the blocks. The blocks are called suborbitals or subshells. I explained on Saturday that shells are the first point of storage of electrons, but shells undergo configuration to give orbitals. To give what? And orbitals finally then give blocks. So electrons are moved from the shell energy level to orbital energy level, and from orbital energy level to the block energy level. Class, when the electrons are still in the shell level, they are the principal level, principal quantum level. Quantum means energy. Quantum means what? Quantum is singular and plural. It means energy level. Class, so electrons can exist in different energy levels. When the electrons are still at the shell level, they are the principal energy level. When they are moved to the orbitals, because class, the shells don't stay at the electrons don't stay at the shells for long. You know, we introduce it to protons, neutron, and electron. We say we have proton, we have neutron, we have electron. That the atoms are made up of 3 subparticles: protons, neutrons, and electrons. The protons and the neutrons are stored deep within the nucleus. They are stored where? Nucleus of the atom. The protons and the neutrons are stored deep within the nucleus of the atom. So those ones are secure. The proton and the neutron are secure. Among the 3 subatomic particles. So we have 3 subatomic particles. I want to get it right. I want to get it organized in your brain and understand it well. We have 3 subatomic particles. Among the 3 subatomic particles, the first 2, proton and neutron, are secured deep within the nucleus of the atom. But the electrons are not secure, hence they don't make up the atomic mass of the atom. If you have to calculate the atomic mass, you will not consider electron. You will say proton plus. The electrons are not secure because they are found outside the shells. And when they are outside the shells, they can easily be lost or gained. I already explained this on Saturday, but as I usually do, anytime I'm teaching a new class, I try to go back a bit so that anybody that missed that last class can still follow up. If I just say to continue exactly where I stopped on Saturday, some people will be lost in this class. So class, I'm just trying to give you a prelude to what we're about doing. So the electrons are not secure. The electrons are not because they're outside the shells. And the funny thing is that the shells are not even the final point of storage of electrons, class. Of course, we have 4 shells, K, L, M, N shell. And each shell has the number of electrons they can contain. But the shells undergo configuration to give orbitals, S, P, D. And each orbital has its own shape, unlike the shells that are all just spherical. Each orbital has its own shape. Class, the shape of an S orbital is spherical in shape. The P orbital has a dumbbell shape. Has a what? And what's the name of the S orbital? I told you on Saturday, sharp, right? S stands for sharp, P is principal, D is diffuse, F is functional. Now, D orbital, please, any class you miss, at least do yourself a favor by following up the class online. You can see that I just started this class and it's being recorded. All classes, any possible class you must have missed, must have been recorded. I think for the past 3 weeks or 4 weeks consecutively, I've made it a point of duty to record all our classes because it's normal that we have different departments in 100 level. Different departments have different schedules, so it's impossible to have everybody in class at the same time. No matter the time you fix, no matter the time you... So this can help those that are not able to make it some days, or you have a practical, you have an assignment, you have one thing or the other. The class is recorded for you so that you can access it. Just make sure you're on the registered members group, because every day I make sure, even if I forget to post in any other group, that registered members group, I always post the updated class there. Any class I teach is always uploaded there on our registered members group, so that our students that are paid will not be missing out. D orbital is double dumbbell. And the F orbital has a complicated shape. Sometimes you see multi-dumbbell, multi-what? These are the shapes of the 4 types of orbitals. I didn't mention this on Saturday, so please take notes. All these orbitals have their shapes. And just like the shells have the number of electrons they can store, the orbitals also have the number of electrons they can... Class, the s orbital can take 2 electrons maximum. That means the s orbital cannot exceed 2 electrons. The p orbital cannot exceed 6. The d orbital cannot exceed 10. So it can take less than 10, but the optimal number of electrons it requires to be fully happy is 10. F is 14. F is what? All these things we did on Saturday. So when the electrons are in the orbital level, we are talking about the azimuthal level. Then when the electrons are in the magnetic level, we are not talking about the blocks. So class, from SPDF orbital, we have what we call SPDF blocks. So S orbital produces S block, P orbital produces P block, D orbital produces D, F orbital produces F block. In order to fully understand the blocks class, the S block contains only 1 block. The P block contains 3 blocks class. The D block contains 5. And the F block contains 7 blocks. Class, each block can take 2 electrons maximum. Each block can take what? So if S block has only 1 block and it can only take 2 electrons, that's 1, 2. You see that S block can take maximum of 2 electrons. The P block has 3 blocks, but each block can take 2, right? 1, 2. So P will take total of what? Because each block is 2 and you have 3. 3 times 2. The D has 5 blocks. So 5 times 2. 10. F has 7 blocks. 7 times 2. So you can see how each of these blocks, this is how we explain the maximum number of electrons each block can take. This is how we explain the maximum number of electrons each block can take. At the block level, you have moved to the magnetic. Class, if you are being asked what is the final point of storage of electrons, is the block. Most people think it's shell. No, shell give rise to orbitals. Because orbitals are formed from shells, another name for orbital is what? Sub-shells. Orbitals are also called sub. Because orbitals are formed from shells, they are called subshells. Because blocks are formed from orbitals, they are called suborbitals. They are called suborbitals or sub-subshells or sub-subshells. Please take note. Class, we said the principal quantum number tells us the number of shell. I explained that we have 1 means first shell, 2 means second, 3 means third. And class, the higher the number of shell, the higher the energy level. Class, an electron that exists only in the first shell will have a lower energy level than those that exist in the second shell and those that exist in the third. So class, if you see K shell, you see L shell, you see M shell. Class, this K shell has the lowest energy level. followed by L shell, followed by M. So this is first shell, second shell, third. So as the number of shells is increasing, so is the energy level, class. So is the energy. So an electron that exists as a principal quantum number of 1 has a lower energy level compared to that has principal quantum number of what? 3. Because when an atom or an electron has a principal quantum number of 3, we are just telling us that that electron exists in the third shell. That electron exists where? In the third shell, energy level. So the principal quantum number gives us the shell energy level. Now the azimuthal quantum number, as I said, so the principal quantum number starts from 1, 2, 3. So class, you can have a principal quantum number of 0. Because your principal quantum number must start from 1, 2, 3, and you keep going up. You can't have 0, you can't have. But for the azimuthal quantum number, you can have 0, class. The azimuthal quantum number starts from 0, 1, 2, 3. Because class, your azimuthal quantum number must always be one number, at least one number less than the principal. Class, if someone's principal quantum number n is 1, class, the azimuthal quantum number L can never be 1. It must be at least n minus. So if you ask to write the mathematical relationship between azimuthal quantum number and principal quantum number, there you go, class. This is it. What's the mathematical relationship or the formula that relates azimuthal to principal? Class, azimuthal quantum number L is equal to the principal quantum number n minus. So at no point should the principal and azimuthal be the same, class. The azimuthal must always be at least one number less than the principal. The azimuthal must be one number less than the. It can be more than one number less, but at least one number. Why am I saying this, class? Because if someone's principal quantum number is 3, for example, what are the possible azimuthal quantum number? 2, 1, 0. 2, 1 what? 0. At least one number less than 3 can go. If you are 2 numbers less than 3, you are still good. If you are even 3 numbers less than 3, you are still. Class, the lowest azimuthal, possible azimuthal quantum number is 0. You cannot have a number less than 0 for azimuthal, class. And when someone's azimuthal quantum number is 0, it represents a particular orbital. If you are told that azimuthal quantum number is 0, class, it means that the electron is existing in the S. If the azimuthal quantum number is 1, it means that you are dealing with the P. If azimuthal quantum number is 2, you are dealing with the D. And if azimuthal quantum number is 3, you are dealing with the F orbital. So class, if you are told that the azimuthal quantum number of an atom, L, is 0, just know that the orbital designation is S. Is what? S. If the azimuthal quantum number is 1, just know the orbital designation is what? P. 2, D, 3, F. Very, very important. So you can see how the azimuthal depends on the principal. In what way? Azimuthal equals to principal minus. Do you know that the magnetic also depends on the azimuthal? The magnetic also depends on the what? Class, the value of the magnetic is, the possible values of your magnetic is all numbers ranging from the negative azimuthal to positive azimuthal quantum number. Class, you cannot get your magnetic quantum number if you don't know your azimuthal quantum number. And you cannot get your azimuthal quantum number if you don't know your principal quantum. No. You see how each depends on the other. Class, you cannot get your magnetic quantum number if you don't know your azimuthal. Because your azimuthal quantum number, class, so this is azimuthal, right? Now, class, when L is 0, your magnetic is just 0. It's just what? 0. There's no other number as 0. 0 is 0. Now, but when L is 1, your magnetic, so this is azimuthal, right? This is azimuthal, and this is magnetic. The lowest possible azimuthal is 0. So when your azimuthal is 0, your magnetic is 0. When your azimuthal is 1, your magnetic can be minus 1, 0, 1. Your magnetic quantum number can range from minus 1, 0, and when your azimuthal is 2, your magnetic ranges from all numbers from minus 2 to plus 2. Minus 2, minus 1, 0, 1. When your azimuthal is 3, your magnetic minus 3, minus 2, minus 1, 0, 1, 2, 3. So you can see that it is the value. So class, this understanding is very vital. And class, watch. Did I tell you that the principal is shell, right? Azimuthal is orbital. You can see that I say when L is 0, it tells us to know that it's S. L is 1, orbital P. L is 2, D. L is 3. Now let me show you how magnetic helps me to know the block class. Every magnetic quantum number here, this is a magnetic quantum number, right? They represent a block. Like look at 0, magnetic 0, we have S block. S. Why do we have only one magnetic quantum number for when L is 0? Because for when L is 0, we have S. And S block has only one. Plus, when L is 1, we have P, right? How many blocks that tell you that P has? 3. Are you saying that we have 3 magnetic for the 3 blocks? We have 3 magnetic for the 3. How many blocks that tell you that D has? 5. How many possible magnetic quantum number do we have when we have this? 1, 2, 3, 4. 5. We have 5 magnetic quantum number for the 5 D blocks. For the 5D, how many blocks that tell you that F has? 7. And we have 7 magnetic quantum number for the 7 F blocks. For the 7 F. So you see that it correlates. So class, now I also told you that each of these blocks has a name, class. Of course, the S block is just called S block. But at least up to the D block, nobody will ask you for the F block, but up to the D block, you must be able to know the name of each block in the P block and the D block. S block is S block, but look at P block. P has 3 blocks. Each of these P block class, this -1, this 0, and has a name, PX, PY, PZ. Why is it important that you know this PX, PY, PZ? Because class, what are these numbers on top? Magnetic, right? These numbers on top are the magnetic quantum. Class, if you are told that the principal quantum number of a particular electron or atom is 2, after principal, what do you have? Azimuthal. And the azimuthal quantum number is 1. And the magnetic quantum number is 0. You could be asked to write down the correct orbital designation given these particular parameters. Write down the correct orbital designation. Class, first of all, you will say 2, meaning the principal number of shell is 2. When L is 1, you're dealing with a P, you're going to write P. But when M is 0, which of the P? Because we have PX, PY, and PZ. It's P. When M is 0, we have P. Class, this is the final answer to this question. When they say write down the orbital designation, given that the principal quantum number is 2, the azimuthal quantum number is 1, and the magnetic is what? 0. Write down the orbital. You will say 2 because the shell is 2. Class, you cannot just write P, Y. Because class, even this P, every orbital comes from a particular shell. So putting these 2 here is telling you that this P came from the second. Don't forget that shell give rise to. So it's wrong to write orbitals alone without including the shell that the orbital came. So this 2 you're writing before P is telling you that this P came from the second shell. But this Y you're writing is which of the blocks of P does this P belong? P, Y. So magnetic tells us the exact block of P where the electron is stored. The magnetic tells us the exact block of P where the electron is stored. D has 5 blocks. And the 5 blocks of D has all their magnetic quantum number. Magnetic, -2, right? Minus 0, 1, and each of these blocks have a special name. This block is called DXY. This block is called DXZ. This block is called DY. This block is called dx squared minus y, and this block is called dz squared. Last question. Last question. So if you are told that when n is 3, for example, when n is what? Principal. L is 2 azimuthal. L is 2 what? And M is minus 1. And M is what? Right hand the orbital, there's a... You must first write the shell where the orbital belongs, right? 3 is the shell that produces the orbital. Now, what kind of orbital is produced when L is 2? D. Now, which block of D is the electron stored exactly? M minus 1 means what? So 5dx. This is the orbital designation for these parameters. For this what? Let's now introduce the spin class. Let's introduce the what? Spin class is now telling us the orientation of the electron in the block. So let us start this journey again. This story started from electrons in the shell. From shell moved to orbital. Orbital moved to block. And spin now tells us in the block. The block, that's which block is the electron stored exactly. So this one tells us that it's in D block. Azimuthal. L is 2 is in D orbital, block orbital. But magnetic tells us which of the block, which of the what? Block. So azimuthal tells us that it's D, magnetic tells us the block in D. Spin tells us how is the electron orientated inside the block. Right, they give you n equals to 3, L equals to 2, M equals to minus 1, and MS equals to plus 1 over 2. MS equals to what? Class, they've just given you the full 4 quantum numbers. Principal, azimuthal, magnetic, spin. They are just giving you the full 4 quantum. As a matter of fact, anytime you see plus 1 over 2, it means that only one electron is inside the block. And that electron is orientated upwards or clockwise. I think on Saturday I also told you that electrons have 2 possible orientation in the block, right? You have the upward orientation or the downward. The upward also called the clockwise, downward also called anti. Class, we use plus 1 over 2 to represent the upward direction. And we use minus 1 over 2 to represent the downward. So anytime you are given a spin quantum number and they give you the spin of plus 1 over 2, just know that that electron in the block is orientated up. If they give you MS plus 1 over 2 and minus 1 over 2, just know that that block is completely filled up. 1 up, 1. If they give you plus 1 over 2 only, know that that electron is just 1 and is orientated upward. If they give you minus 1 over 2 only, just know that electron is orientated down. Now, very, very what? Important. Very, very what? So the spin quantum number just helps us to know the orientation of the electron in the block. Now, class, they can ask you to calculate the maximum number of electrons. Class, there's a formula to calculate the maximum number of electrons, but the formula changes depends on what they give you, class. The formula for maximum number of electrons in an atom is 2 raised to power 2n all squared. 2n all, where n represent number of shell, where n represent number of what? If you have to calculate or determine the maximum number of electron, where n is 1, class, 2 into bracket 1, or what is 1 squared? 1, 2 times 1. So the maximum number of electrons, when the principal quantum number alone is given as 1, is 2. The maximum number of electrons, when the principal quantum number alone is given as 1, is what? When n is 2, you say 2 into bracket 2, or you get another answer. When n is 3, get another. But class, please note, this formula will not always work because this formula will only be used when you are given n only. Class, as soon as they give you n and l, for example, find the maximum number of electrons when n is 2 and l is 1. Find maximum number of. Now someone will go and say, okay, this is the formula 2n squared. And n is 2. Say 2 into bracket 2 or 2 squared. 4 times 2. You say 8 is maximum electron, it's going to be wrong. It's going to be, you know why? When we use n only then, it was because n was the only information they gave us. But if they go ahead to give you the orbital class, you will bypass the number of shell and go to the orbital. When L is 1, what orbital are you dealing with? P. You're dealing with what? And for P, what's the maximum of electron a P block can take? 6. You can take what? 6. So the total number of electrons for this kind of question is 6. Even though the formula is 2n raised to square. But class, 2n squared is only used when n alone is given and there's no L, there's nothing else. So at this point, the only information you have is the number of shells. So the maximum number of electrons when the number of shells is 2, you get 8. But when they go ahead to give you further information, class, it means that this particular shell contains 2 electrons but produces the P. So what's the number of electrons the P shell can take? Now, if they go further to even give you further information, and they say when n is 2, L is 1, and M is 0. And M is what? 0. They have gone further to give further information. You will bypass this and go to this place. When M is 0, which block are we dealing with? This Px, Py, P. So this is minus 1, 0, and. So in the 0 block, how many electrons can the 0 block take? Total number of electrons is what? 2. Total number of electrons is what? 2. Because they are giving you more info. If they now go ahead and give you ms as plus 1 over 2, it means they are already giving you the number of electrons, just 1 electron. ms means that there's only 1 electron inside that block, because plus 1 over 2 means there's only 1 electron, even giving the orientation of the electron is upward, right? But if they give you plus 1 over 2 and minus 1 over 2, it means there are still 2, one oriented upward and one oriented downward. Class. The following are incorrect sets of quantum number. The following are incorrect sets of quantum. The following are incorrect sets of quantum number. The following are incorrect set of quantum number. N, L, M, and MS. The following are incorrect sets of quantum number. N, L, M, L, and M. The following are incorrect sets of quantum number. N, L, M, L, and MS. Class, note that N represents azimuthal magnetic spin. Give the corrections in each set, assuming N is always correct. Give the corrections in each set, assuming N is always correct. Give the corrections in each set, assuming N is always correct. Give the corrections in each set, assuming N is always class. Give the correction in each set, assuming N is always. They intentionally gave us some set of wrong combination of quantum number. They asked us to figure out what is wrong in each of these arrangements. What is wrong in each of these? Plus, assuming the n, the first number is n, right? So the first number is here at the n, this L, this ML, magnetic, and this is the spin, right? So this side is the spin, spin, spin. So the first three are principal, azimuthal, magnetic, then this is the spin. Class. What, have you seen anything wrong with this? Is the principal quantum number is always correct? They said that, right? Assuming n is always this, okay, right? Azimuthal should be one number less than the principal. If azimuthal is 0, magnetic is also 0. You know that, remember? Yes. What kind of orbital is this? S. S. Coming here now, this word is wrong, class. Class, according to Pauli's exclusion principle, according to Pauli's exclusion, it is wrong for 2 electrons in a block. Class, a block can only take 2 electrons, right? Class, no 2 electrons should have the same spin. That means no 2 electrons should be facing up. If one is up, one must come. If one is down, the other will go. It's wrong for 2 electrons to be upward. Class, plus 1 over 2 plus another plus 1 over 2 indicates that the 2 electrons are upward. Did you see? You saw. Giving it. Plus 1 over 2 and another plus 1 over 2 indicates that the 2 electrons are. So what is wrong with this is what? This one of them was what? Minus. One of them was B. Let's go to B, class. Let us go to B. Class, what is wrong with this already? The azimuthal, right? Yes. Our azimuthal cannot be the same with our principal. It must be at least one number less than the. Our azimuthal must be one number less than the principal. So, class, these two must at least be 1. Must at least be what? Can it be 0? No. You know why it cannot be 0? If it's 0, my magnetic will have to be 0. So it is 1. It's definitely. Let's go to C. What's wrong with C? Principal is 3. Always correct. Can our azimuthal be 0? Yes. Our principal can be 0, 1, 2. But it can never be 3, right? It can be 0, 1, 2. It can never be. But if our azimuthal is 0, then our magnetic should also be what? This can be correct, meaning that it's just one electron, right? And it's facing up. Correct, right? This guy is correct. This is 2 principal. 1, azimuthal can be 1. Magnetic can be minus. Minus 0 means that there is no electron. There is no electron in the block. Class, a block can be empty, class. A block can be. If you have plus 1 over 2, it means that there is one electron facing upward. If you have plus 1 over 2 and minus 1 over 2, it means there are 2 electrons in a block. One is going up, one is going. But if you have 0 as spin, it means that there is no electron. It's empty. The block is. So, class, nothing is wrong with D. Nothing is wrong with. So, class, your spin can be 0. Your spin can be what? 0 simply indicates that there is no electron in the block. There is no electron in the. Let's come to E now. Principal is always correct, 3. Azimuthal is correct, 2. Magnetic cannot be 3, right? Yes. Magnetic must range from minus 2 to plus. Magnetic must range from minus 2 to plus. But class, since we cannot exactly specify who will be the magnetic, we are going to write the full number, minus 2, minus 1, 0, 1. It could be any of this, right? Any of this could fill up this space. And class, we're done with that aspect. On Saturday, we have already done electronic configuration, right? SPDF, noble gas configuration, right? If you miss the class, please watch the video. Very important. Class, we have said that let's look at application of electronic configuration. Right, the application of electronic what? Application of electronic configuration. Application of what? So class, what this means is that if I ask you to write the SPDF configuration for any element, you can do it, right? For example, write down the SPDF configuration for zinc, which is 30. SPDF configuration. Remember, I gave you that table. I said 1s, 2s, 2p, right? 3s, 3p, 3d. 4s, 4p, 4d, 4. 5s, 5p, 5d, 5. Class, we fill from lower energy level before higher energy. When filling electrons in orbitals, we start filling from the lower energy level before we go to the higher energy. So you fill 1s first. After you fill 2, then you fill 2p and 3s. Then you come 3p and 4s, 3d, 4p, 5s, 4d, 5p, 4f, 5d, 5f. If I want to continue, I can still continue. I'll put 6s, 6p, 6d, 6f. So if I want to fill 30, what is the electronic configuration for 30 SPDF? 1s, start filling from 1s. S can take only 2. After 1s, you go to 2s, 2s. After 2s, when you go to 2p, 2p. P can take up to 6, remember. After 2p, 3s, S can still take 2. 3p, 4s. After 4s, what's next? 3d, 10. This is 30. Class, so stop as soon as you have achieved 30. Stop as soon as you have achieved 2 plus 2, 4. 4 plus 6, 10. 10 plus 2, 12. 18, 20 plus 10, 30. This is the SPDF configuration for zinc, class. Class, the electronic configuration of an element can help us to determine a lot of things. That's why we're looking at application of electronic configure. One is that it can help us to determine the period of an element in the periodic table. Period. You could be asked, what period does zinc belong in the periodic table? 2. It can help us to determine the block if the element belongs in the periodic table, the block. And 3, it can help us to determine the group the element belongs in the periodic. These are 3 applications of electronic configuration. These are 3 applications of what? Electronic configuration. The SPDF configuration of an element can help us to determine the period of the element, the block the element falls under in the periodic table, and the group. And the what? So what I want to show you now is how do we use this SPDF configuration to determine the period. Class, I can as well tell you that the period that zinc belongs in the periodic table is period 4. Is period what? When you write down the SPDF configuration, just write down the highest number. 4. Period what? 4. It can also help us to determine, if they say write down the electronic configuration for sodium, Na is 11. 1s2, 2s2, 2p6, 3s1. 1s2, 2s2, 2p6, 3s. What we did zinc? Zinc was 1s2 is 30, 2s2, 2p6, 3s2, 3p6, 4s2, 3d. And we said that the period that zinc belongs is the highest number in the periodic configuration, which is 4. So with this, I can say that the zinc belongs to period. What block does zinc belong to? Zinc belongs to block S. The block that this 4 is carrying is the block it belongs to, S block. Zinc belongs to S. Because class, your periodic table is divided into 4 blocks. S block elements, P block elements, D block elements, and F block. Your periodic table is divided into groups and periods, and also divided into blocks. Some elements fall under the S block, some elements fall under the P, Some elements fall under the F block and some fall under the D block. Class, application of electronic configuration can help us to determine the block an element falls under. Class, go to the highest shell, which is 4. What block is it carrying? S is the block the element belongs. Now, what group does the element belongs to, class? Go to the highest shell, 4. And what's the number on the block? 2, class. Class, I can tell you that zinc belongs to group 2 in the periodic. So, the period 4, block S, group. Class, I can bet you could be given an element in the exam and asked to classify the period, block, and group of the elements. Class, without this method, you would have had to draw the full periodic table of 110 elements in an exam hall. That is if you even remember all the 110 elements. This is almost like a shortcut to determine the period, block, and group of any element. The period, block, and group of any element. As long as you can write down the electronic configure, you can bring out what group does it belong, what period does it belong, and what block does it. Let's apply same to sodium, class. From your understanding, what period will what period of sodium belong in the periodic table?
3.
Period
3.
For the S number is 3. What block?
S.
S block. What group?
Group 1.
Sodium is in group. Sodium is in group. Let us look at someone like, give me an element. Let's look at ion, Fe. Ion is 28, right? 1s2, 2s2, 3s2, 3p, 6, 4s2, 3d8. 3d what? Period 4, ion belongs to period 4. Ion belongs to group 2. Ion belongs to what? Group 2. And ion belongs to the S block. S block. So with the electronic configuration, we can determine any block that an element. I missed something. Okay, 1s to 2s to 2p, 6, right? 3s to 3p, 6, 4s to 3d, 8. Class, for ion, please, I made a mistake for ion. Ion actually belongs to the D block. The last block that receives an electron is the block that the element belongs to. Please take note. The last block that received is the block that the element belongs to, please. I was thinking I was using the last shell. This will help us know the shell and the group. But the block is the last block. Please, same with zinc. Please, same with zinc belongs to the D block. Zinc belongs to the what? The last block that receives an electron determines the block that the element belongs to, the last block. But for the period and group, yes, 4 and 2. Now, let's write down the periodic table. Let's go to the periodic table. Let's look at the modern periodic table. Right, and the periodic table is an arrangement of elements in order of increasing atomic number. Periodic table is an arrangement of elements in order of increasing atomic number. Periodic table is an arrangement of what? Elements in order of increasing atomic number. Periodic table is an arrangement of what? Elements in order of increasing atomic number. The modern periodic table is guided by the periodic law. The modern periodic table is guided by the periodic law. The modern periodic table is guided by the what? Periodic law. So write down the periodic law. Let's take the periodic law. The modern periodic table is guided by what? The periodic law. The periodic law states that the chemical and physical properties of elements are a periodic function of the atomic numbers. The periodic law states that the chemical and physical properties of elements are a periodic function of the atomic numbers. The chemical and physical properties of elements are a periodic function of the atomic numbers. Are a periodic function of the atomic numbers. This implies that elements with the same chemical and physical properties will fall under the same group. This implies that elements with the same chemical and physical properties will fall under the same group. Elements with the same chemical and physical properties will fall under the same group. Rather, characteristics of the modern periodic table. Characteristics of the modern periodic table. Characteristics of the modern periodic table. 1. Elements are arranged in rows in order of increasing atomic number called periods. 1. Elements are arranged in rows. Elements are arranged in rows, ROWS, in order of increasing atomic numbers called periods. Elements are arranged in rows in order of increasing atomic number called. The first period contains only 2 elements, that is hydrogen and helium. The first period contains only 2 elements, hydrogen and helium. The first period contains only 2 elements, hydrogen and helium. Class, this is a mini periodic table of the first 20 elements. Class, we're going to use table to explain some things in periodic table. Let's continue first. We said the first period contains two elements, hydrogen and class. So this period 1. How do you check period in a periodic table? You use the horizontal rows. Check them horizontally. The periods are checked white groups are checked what? Vertically. So I've checked what? Let's continue. Say characteristics of the modern periodic table. Characteristics of the modern periodic 3. The second and third periods contain 8 elements each. The second and third periods contain 8 elements each. 1, 2, 3, 4, 5, 6, 7. The second and third period contains 8 elements each. So class, this period 1, this period 2, this period, the second and third period, this first period. This second period, third. The second and third period contains what? 8 elements each. The fourth and fifth period contains 18 elements each. The fourth and fifth period, class, I think we will continue this to the 110 elements. You would have seen it, but you can open any of your textbooks and go through the periodic table and confirm that. The fourth and fifth period contains 18 elements each. The sixth period contains 32 elements. The sixth period contains 32. The sixth period contains what? 32 elements. The sixth period contains 32 elements. The sixth period contains what? And the seventh period is incomplete. The seventh period is what? Don't forget, there are 7 periods in the periodic. There are 7 periods in the periodic. There are what? How many periods, class?
7.
There are 7 periods in the periodic table. We just explain all the 7 periods for you. The first period contains 2 elements. The second and third contains how many elements?
8.
8 elements. The fourth and fifth period contains 18. The fourth and fifth period contains 18. The sixth period contains 32.
Elements.
The seventh period is incomplete, but we are still discovering more elements. Maybe they're discovering more. When we were learning chemistry in year 1 back then, they told us that we had 106 elements. Before we finished, they said they have discovered 4 more, 110. It's possible that we have discovered more now. I'm hearing that they discovered on that planet. You know, when some of you were in secondary, they told you we have how many planets?
9.
9, right? Different discoveries. Several Pluto is gone missing, Abi. Different things are happening in science every day. Different discoveries. Even what is this guy's name? He's planning to make Mars habitable by man. What is his name? Elon Musk. Yes, they are working on it to make Mars habitable by anybody that can make that Mars habitable is the owner of that whole Mars. Because you know that all this land. How do you say this? You spend I own this land. It's first person to get there, right? So that Mars, now nobody's staying there. When one man has now made it habitable now, you see Nigeria is now dragging the place. Why do you not go there since? Someone has now made everything fine. You now say, now we get this land. Now equally land be this. Are we together? Now nobody's going there. Go there now, no way. Once they have walked the place now, you see people dragging the place. So class, each period writer represents the number of shells or energy levels present in an atom. Each period represents the number of shells or energy levels present in an atom. Each period represents the number of shells or energy levels present in an atom. Class, very interesting. Are you aware that all elements in period 2 have 2 shells? So class, the period you belong help me to know the shell that the number of shells the element carries. the period an element falls under helps us to know the number of shells the element has. Class, check all elements in period 2. 2, 1, 2 shells. 2, 2, 2, 3, 2, 4. This is a shell configuration now. 2, 5, 2, 6, 2, 7, 2. Elements in period 1 have only one shell. Iron and have only one, which is the K shell, right? Period 3 have 3 shells. What is configuration for sodium? 2, 8, 2, 8, 2, 8. You can continue it on and on and on, you see? So the period an element belongs to helps us to know the shell, the number of shell or energy level. Now, class, groups. Write down groups. We have just looked at periods. Let's look at groups. Still under characteristics of modern periodic table. Still under characteristics of modern periodic. Let's look at groups, class, groups. Groups are vertical columns in the periodic table. Groups are the vertical columns in the periodic. Groups are the vertical columns in the periodic table. Groups are the vertical columns in the what? Periodic table. Class, today and tomorrow we are doing chemistry. Because Saturday is mathematics shortcuts. We have gone a bit far in physics. So tomorrow I'll still continue chemistry. I'll still continue what? I want to push this chemistry very far too. There was a time we were just doing physics, Abby. So tomorrow push me physics, but we'll do chemistry. We'll do what? I want to push this chemistry very far. Now, groups are the vertical columns in the periodic table. Groups are the vertical columns in the periodic. And there are 18 groups in the periodic table. There are 18 groups in the periodic. Class, there are 18 groups in the periodic table. Groups are also called families, class. Another name for group of the periodic table is what? Family. Please, every key point note it because your exam is subjective. In a subjective exam, a very key point can be asked of you, and if you don't know it, there is no option to remind you. In an OBG exam, even if you don't know it or you have read it before but you forgot, the options can easily remind you of something you have seen before, you have read. But in a subjective exam, there is no option to remind you. So you are left to think of that answer by yourself. So every key point you are mentioning, please, they are vital, class. There are 18 groups in the periodic table, and another name for group is what? Families. 18. There are 18 groups for the whole 110 elements. Class, for these 20 elements, there are 8 groups. But for the actually 110 elements, the full periodic table is 18 groups. And these 18 groups, continue writing, these 18 groups are divided into 2 subgroups. We have subgroup A and subgroup B. These 18 groups are divided into 2 subgroups. Subgroup A and subgroup what? B. Class, elements in subgroup A are called representative elements or the main group elements. They are called representative what? Or the main group element, main group. Elements in subgroup A are called what? Representative elements or the what? Main group elements. Elements in subgroup A are the representative elements, also known as the what? Main group elements, and they are as follows. Group IA, IIA, IIIA, IVA, VA, VIA, VIIA, VIIIA. These ones are called VIA or group 0 or group VIIA or group 0. Come and sit down here. I should be the class report. Come and sit down. Why elements in subgroup B are called transition elements? Elements in subgroup B are called what? Transition. Elements in subgroup B are called transition. Group IA are called alkali metals. Alkali. Group IA are called alkali metals. Group IIA are called alkali earth metals. IIA are called alkali earth. So IA are called alkali metals. IIA are called alkali earth. Class, we said we have 18 groups. Have you noticed that we have just 16 here? 8 plus 8. The remaining 2 groups are called the lactanides and the actinides. The lactanides and the what? They are called inner transition elements. Note, the lactanides and the acti are called inner transition. When you see your main periodic table, you see under 2 people on below. They are just below like this. They are the inner transition elements. So that's what makes up 18. So 8 come from the representative elements. Another 8 come from transition. 8 plus 8, 16. And we say there are 18 groups. Remaining 2 groups. The remaining 2 are the lactanides and the making up 18. What's the name for the lactanides and the actinides? Inner transition. The lactanides and the actinides are also known as inner transition elements. Group 1 are called what? Alkali metals. Group 1, IA. IIA are called alkali earth. IIIA are called the boron family. They are called the boron. So this IA, IIA, boron family. Group IVA, carbon family. IVA are called the carbon family. IVA are called what? Class. This group IIA are also called group 13. Are called what? Group IVA are called group 14. Group what? Are called group 14. So this group 1, this group 2, IIA is group 2, IIA is group 13, IVA group 14, VA group 15, VIA group 16, VIA group 17, and VIIA group 18. This is what? Boron family, this carbon family, this nitrogen family, nitrogen what? So alkali metals, IA, alkali earth metals, IIA, boron family, IIIA, carbon family, IVA, nitrogen family, VA, chalcogen, this one are called chalcogens. Chalco, in exam it can be asked. Group VIA are called, also known as. Then VIIA are called halogens. Are called what? Salt formers. They also known as salt VIIA. They are the halogens, also called salt formers. They form salt. Check most of your salt, NaCl. Salt. VIA is chalcogens. Chalcogens. Chalcogens.
So which group do lactonide and actinide fall under?
No, they are not under these two. They are the last. They are separate. They are called inner transition elements. So if you want to divide elements in the periodic table, you divide them into representative elements, transition elements, and inner transition. The representative elements are what? Are the main group elements. The transition elements are after the representative element. Then we have the inner transition elements. Those ones they are under. They are not part of the major structure of periodic table. You see them. If you have a good periodic table, you see them just below like this. They are the lactonides and the. Let's go to periodicity of elements in the periodic table. Periodic trends. Is there any class by 2? Any lecture by 2? What lecture? CSE. Which other lecture? Periodicity of elements in the periodic table. Periodicity of elements in the periodic table. We want to look at ionic radius, atomic radius, all those things, electronegativity, electropositivity, and how we can determine them. Periodicity of elements in the periodic table. Periodicity of elements in the periodic table. So you can also say this. It's also called the properties of elements. How do elements behave? As their characteristics. Let us start with atomic size or radius. Atomic size or radius. Write down atomic size or radius. Atomic size or this is 1/2 of a distance that exists between two atomic nuclei. Atomic size or radius is 1/2 of the distance that exists between two atomic nuclei. This is 1/2 of the distance that exists between two atomic what? Nuclei. Class, after defining this periodicity, we are going to study the movement of the atomic size of elements across the period and down the. When looking at across the period, we check from left to across the period from left to right. How does atomic size change across the period from left to right? Does it increase? Does it reduce? We'll find out. And down the group, class, we'll look at down the and across the period from left to right. So write a periodic trend. Okay, don't write down. There's no time. Just say atomic size or radius increases down the group but decreases across the period from left to right. Atomic size or radius increases down the group, increases down the group, but what? Reduces or decreases across the period from left to right. Class, from left to right, the atomic size is reducing from left to, but down the group it is what? Increasing. Example, arrange the following atoms in order of increasing atomic size. Arrange the following atoms in order of increasing atomic size. P, S, A, S, S, E. Arrange the following atoms in order of increasing atomic size. Let me explain something to you first. Down the group, atomic size is increasing. Why? Because let's take this group 1 for example. Electronic configuration for hydrogen is 1. So it has just one shell. It has just one, but it has only one electron, right? But lithium has 2 shells, 2, 1. So you are drawing 2 shells. Is there no bigger size already? 2 electrons here and 1 electron outside. Sodium is 281. That's 2, 8, 1. Bigger. Are you seeing how the atomic size increasing from hydrogen to lithium to sodium? So as you are going down the group, the atomic size is what? This guy is 2881. It will be bigger. So if you have to arrange these 4 atoms in order of increasing atomic size, increasing means from smallest to biggest, right? And decreasing means from biggest to smallest. Why is it that you are going across the period, atomic size reducing? Why? Because everybody in this period has the same size. Everybody in this period has the same what? Size. Are you not saying 2, 1, 2, 2? So the same size, because they have the same number of shells now. But class, do you know that why is atomic size reducing then? Because they're going from left to right, the number of electrons is increasing. And the more number of electrons, the more the constriction, the more the electron pull on the atom, thereby shrinking the atomic size. Follow me. Class, someone that has 2, 3 and someone that has 2, 4, they have the same number of shells, right? But this guy has more electron than this. So there's more electron density. The electron density, the higher the electron density, the more the electron constriction. The higher, the greater the electron pull. And the greater the electron pull to this nucleus, the smaller the atomic size. So class, because there's greater electron between in carbon compared to boron, carbon's atomic size will be what? Reduced. But the more number of electrons, the more the electron pull to the nucleus, thereby shrinking the. Are we together? Because all electrons pull the atom to the. So there's more shrinking. So someone that has if 2 atoms have the same size, the same shells, the person with lesser electron is going to be bigger than the person with more. You will not check number of what? That's why as you're going from left to right, atomic size is what? Reducing, because electron is increasing. As electron is increasing, the pull, the atom is reduced. The electron pull is causing the atomic size to what? Reduce. And class, that explains why, if you look at sulfur and phosphorus, first of all, where is sulfur? Where is phosphorus? Sulfur has class, this selenium and arsenium are all families under sulfur. If you continue this chart, you're going to see this. So class, if you look at this now, so if this is 26, this is 286, 2886, the shell is getting bigger, maybe 28818, you understand? Now, the shell is getting bigger. So they ask us to arrange an increasing atomic size. First of all, between phosphorus and sulfur. Phosphorus is 285. Among these 4, sulfur has the lowest atomic size, first of all. Because between sulfur and phosphorus, between sulfur and what? Sulfur has more electrons. Even if they have the same number of shells, sulfur has more, so there's more electron pull here. Therefore, phosphorus is a bigger atomic size. So sulfur is smaller atomic size than, that's why sulfur is the one that started. In increasing, that's from smallest to, after sulfur is phosphor, after phosphorus, you now have this, and this guy is the biggest atomic size. Now, arrange the following in order of increasing atomic size. Carbon, aluminium, oxygen, potassium. Let me see if you get it. Carbon, aluminium, oxygen, potassium. Arrange in order of increasing atomic size. It was not playing. was not playing. More pull here than here. Are you together? One more class. Are they the following in order of increasing atomic size? Are you ready? Oxygen, sodium, magnesium, sulfur, lithium. Oxygen, sodium, magnesium, sulfur, lithium. Oxygen, sodium, magnesium, sulfur, lithium. Oxygen, sodium, magnesium, sulfur. Arrange in order of increasing atomic size. Increasing means from smallest to, who is the smallest? Oxygen is 2,6, sodium is 281, magnesium is 282, sulfur is 286, lithium is 21. Lithium is 2. Who is the smallest? Oxygen. Is what? Between oxygen and lithium, oxygen is the smallest, right? Because it has more leg. So oxygen is less than lithium. Now, between sodium, magnesium, and sulfur, they have the same number of shells, right? So which is the smallest? The person with more electron, right? Sulfur, magnesium. So you have now understood it, Abby? Good. You have understood. Let's go to our ionic size. There's one between atomic size and ionic. Write down ionic size or ionic radius. Ionic size or ionic radius. Ionic size or ionic radius. Please, be fast. Permit me. I want to finish. I want this video to end everything in periodic table. I don't want to cut. If I stop this class now, I will cut it. Next, I'll not do video periodic table again. Let everything periodic table be in this video. But I'm almost done. Once we finish all this periodicity, we are done with periodic table. So in the next class, I will teach Lewis structure tomorrow. Chemical bonding and Lewis. So tomorrow we are teaching chemistry. Chemical bonding and Lewis structure. So let everything in periodic table end today. So tomorrow I'm coming for a new. So the video will not be divided into two. If I stop now and I've not finished periodic table, so now let everything in periodic table be in this video. Ionic radius, also known as ionic size. Note, ions are formed by removal or addition of one or more electrons to an atom. Ions are formed by removal or addition. Ions are formed by removal or addition of one or more electrons to an atom. Ions are formed by removal or addition of one or more electrons to an atom. When a positive ion is formed, the number of positive charges on the nucleus exceeds the number of electrons. When a positive ion is formed, the number of positive charges on the nucleus exceeds the number of what? Electrons. When a positive ion is formed, the number of what? Positive charges on the what? Nucleus exceeds the number of what? And since the proton is greater than the electron, this will result in the electrons being pulled in. Thereby reducing the size. This will result in the electrons being pulled in, thereby reducing the size. This will result in the electrons being pulled what? Thereby reducing the size. Therefore, a positive ion is always smaller than their corresponding atom. Therefore, a positive ion is always what? Smaller than their corresponding atom. What do I mean? If you compare sodium and sodium plus, who is smaller? Therefore, a positive ion is always smaller than the corresponding atom. Class, even without using this complicated reason, because I'm sure this reason, if you look at it very, you might be confused, right? Let me give you a simpler reason. Why is Na plus smaller than Na naturally? Na means 2,8. Na means what? Well, Na plus means that sodium has lost 1, so it's just 2,8, right? So class, even by using normal common sense, who is smaller? This is 3 shells, this is just 2 shells. Who is smaller? This, right? So class, the logic is this. For positive ions are usually smaller than their corresponding counterparts. But for negative ions are usually bigger than their corresponding. Class, a sodium ion is smaller than normal sodium, uncharged sodium. But chlorine ion is bigger than uncharged chlorine. Uncharged what? Chlorine. So right, negative ions are always bigger than their corresponding atoms. Negative ions are always bigger than their corresponding atoms. Class, note that ionic radius has a similar trend to atomic radius or atomic size. Ionic radius has a similar trend to atomic radius or atomic size. But class, usually when we are arranging elements in order of increasing ionic radius, we don't use the periodic table. We don't use the what? Why? Because our periodic table is mostly consisting of uncharged elements. Uncharged. Class, what we do is we use our common sense of ions. For example, let me give you an example. Arrange the following atoms and ions in order of decreasing size. In order of decreasing. Arrange the following atoms or ions in order of decreasing size. Decreasing means IS2, Mg2 plus, Ca2 plus, Ca. Arrange them in order of decreasing size. That means from biggest to. Who is the biggest? Who has the biggest size among these three? Class is obviously calcium is greater than. Now between Mg2 plus and Ca2 plus. Between Mg2 plus and Ca2, Mg2 plus means magnesium has lost 2 electrons to become 2,8. Ca2 plus means calcium has lost. Calcium normally is 2,882. It's number 20, so it is 288, but calcium 2 plus means it's now 288. 2 electrons are gone, right? But 288 is still bigger than 28. So it's Ca, then Ca2 plus, then Mg2. We are going from biggest to arrange in order of decreasing size, from biggest atomic size to smallest atomic. So Ca is bigger than Ca2 plus, bigger than Mg2. Write down isoelectronic species. Isoelectronic species. Isoelectronic species. Isoelectronic species are species that contain the same number of electrons. Isoelectronic species are species that contain the same number of what? Electrons. Isoelectronic species are species that contain the same number of electrons and therefore have the same electronic configuration. Isoelectronic species are species that contain the same number of electrons and therefore have the same electronic configurations. Example of isoelectronic species: lithium plus, Beryllium 2 plus helium. Plus, all these guys have 2 electrons. They have what? So they are isoelectronic. Once you have the same number of electrons, 1, 2 or more species. When you have 2 or more species with the same number of electrons, they are called isoelectronic. When 2 or more species have the same number of electrons, they are called what? Isoelectronic. Lithium plus means that lithium has lost 1 electron to have only 2 electrons, right? Beryllium 2 plus means that beryllium has lost 2 electrons to have only 2. And of course, we already know that helium just has 2 electrons. So isoelectronic species are species with the same number of what? Under example of isoelectronic species, we have Na plus, Mg2 plus, neon has 10 electrons, Al3 plus. All these guys are isoelectronic. All these guys are iso what? Electronic. They have the same number of electrons. When sodium loses 1 electron, he has 11 electrons. When he loses 1, it becomes. Magnesium has 12 electrons. When he loses 1, then he loses 2. 10. Neon is 10 electrons normally. Aluminum has 13 electrons. When it loses 3, 10. Isoelectronic. Note, for isoelectronic species, because class, you could be given isoelectronic species and asked to arrange them in increasing size. They have the same number of electrons, right? How do we now know who is bigger? Write down. Note, for isoelectronic species, the number of electrons remains constant. The number of electrons remains, but their protons differ. That's the atomic number. But their protons differ. For isoelectronic species, the number of electrons remains constant, but their protons do what? Differ. But their protons differ. For isoelectronic species, the number of electrons remains constant because the isoelectronic means that they have the same number of electrons, but their protons differs. So therefore, the size of the isoelectronic species decreases as the atomic number increases. The size of the isoelectronic species decreases as the atomic number increases. The size of the isoelectronic species, the size of the isoelectronic species decreases as the atomic number increases. The size of the isoelectronic species decreases as the atomic number increases. The size of the isoelectronic species decreases as the atomic number increases. So the more the atomic number, the lesser the size. The lesser the what? Arrange the following in order of decreasing size. Arrange the following in order of decreasing size. Class, all these guys are isoelectronic. All these guys are what? All these guys are isoelectronic because phosphorus is number 15. 3 minus means he has gained 3 electrons to have 18 electrons. Sulfur is number 16. 2 minus means he has gained 2, 16 plus 2. Cl minus, chlorine is 17. Minus 1 means he has gained 1 electron, 18 electrons. Potassium is 19. 19 plus minus 1. 19 minus 1. Plus 1 means you have lost 1 electron, right? Plus 1 means you have lost. Minus 1 means you have gained. Calcium is 20. But plus 2 means you have lost 2. 20 minus 2. They all have 18 electrons, so they are isoelectronic. So we need another man. How we now know who is bigger size? Class, the atomic number is inversely proportional to the size. The atomic number is inversely proportional to the size, or the size is inversely proportional to the atomic number. Those that have a bigger atomic number will have a smaller size. Class, what's the atomic number of phosphorus? 15. Sulfur? 17. 19. So the social arrangement, is it increasing or decreasing?
Decreasing.
Decreasing means who has the biggest size? The person that has the biggest size, the person that has the what? Smallest atomic number, which is phosphor. Oh, I've already arranged them in small, right? In decreasing, it's already arranged. Already what? Because the isoelectronic, they have the same number of electrons. There's no medium to know who is smaller or bigger except to use the atomic number. So the smaller the atomic number, the bigger they will give some people this in the exam. They will not know what criteria to use. Hey, they'll just guess, arrange them anyhow. You might not understand what we are teaching you till you go to exam questions. Arrange the following in order of increasing the electronegativity. What should I use? And check these ones. We are not using down the group to even solve it across the period. You must know something you are using to solve for them. Ionization energy, next. Ionization. This is the energy required to remove the most loosely bound electron from an isolated gaseous atom. This is the energy required. This is the energy required to remove the most loosely bound electron from an isolated American communicate. This is the energy required. Ionization energy. Ionization what? Energy. This is the energy required to remove the most loosely bound electron from an isolated gaseous atom. This is the energy required to remove what? The most loosely bound electron from an isolated gaseous atom. This is the energy required to remove the most loosely bound electron from an isolated gaseous atom. Note, ionization energy increases across the period, increases across the, and decreases down the. Ionization energy increases across the and decreases down the group. Also note that the smaller the atomic size, the higher the ionization energy. The smaller the atomic size, the higher the ionization. The smaller the atomic size, the higher the ionization energy. The smaller the atomic size, the higher the ionization. That is, ionization energy increases as the size of the atom decreases. That is, ionization energy increases as the size of the atom decreases. That is, ionization energy does what? Increases as the size of the atom decreases. Ionization energy increases as the size of the atom decreases. Arrange the following in order of increasing ionization energy. Arrange the following in order of increasing ionization energy. A in bracket 0.32. B in bracket 1.46. C in bracket 0.72. D in bracket 1.02. E in bracket 0.66. F in bracket 1.48. Arrange them in order of increasing ionization energy. Class, what they put in bracket is the atomic size. The atomic what? Class, who should have the biggest ionization energy? The person with the smaller atomic size. The smaller the atomic size, the bigger the ionization. The smaller the atomic size, the bigger the ionization. So who have the biggest ionization energy? 3.3. Because class, they did not mention the name of the element, so you cannot use periodic table to determine it. For secondary school, if they give you the element, you say increasing this thing, you will not check it in the periodic table, right? But who do you know as A? You don't know. Who is B? You don't. So you must use the atomic size to determine who has the biggest ionization energy. Did they say increasing or decreasing? Increasing or that means from smallest to. So who has the smallest ionization energy? Who has the smallest ionization energy? 1.4. The person with the biggest atomic size will have the smallest ionization. So So 1.4 is F, smallest, B, less than D, less than C, less than E, less than A. So A has the biggest ionization energy because he has what? The smallest atomic size. A has the biggest ionization energy because he has the smallest what? Atomic size. Arrange the following in order of increasing ionization energy. Ne, Na, P, Ar, K. Arrange in order of increasing ionization energy. Ne is neon, right? In increasing ionization energy, this one will not use atomic size. We will use the periodic. What do we say happens to ionization energy in the periodic? We increase across the, reduces down the. So across the period, ionization energy increases. Class, who has the highest ionization energy among these? Down the group is increasing, right? Sodium and potassium belong to the same group.
Decreasing down.
So it's decreasing down the group. Means that as it's coming down, it's reducing. So it means that sodium has a higher ionization energy than potassium. As it's coming down, it's reduced. So potassium has the lowest ionization energy. But they're going from left to right is increase. Where's neon? Neon has a very high ionization what? As they're going from left to right is increasing, right? Neon has a very good ionization energy. Sodium is, where's sodium? Where's phosphorus? Look at sodium, look at phosphorus. What am I trying to do? I'm trying to use the atomic size. See, like this will confuse you. How do you know? One is down, one is up. I'm trying to use the atomic. Thank God I taught you and explained the atomic size to you very well, right? Can we arrange this equal in the let's arrange them in order of who has the smallest atomic size? Who has the smallest size?
K, potassium.
No, not potassium. The more the number of shells, the more the size, remember? The more the number of shells, the more the... Who has the smallest size? You forgot it now. It's neon. Neon has the smallest. Followed by who? Argon. Because between sodium and this, they have the same number of shells, right? The person that has the more electron has more electron, so it has a smaller size. Followed by argon. So class, this person has the biggest size, right? Because he has the biggest size, he will have the smallest ionization. The bigger the atomic size, the smaller the ionization. So he has the biggest size, but the smallest. So to get the smallest, now you now revert it now. So for ionization energy is going to be K, Na, P, Ar, N. Who's getting it? You're getting what I'm doing? Good. I'm using the atomic size. Remember, the atomic size and ionization energy are opposite ends. They are inversely proportional. When one increases, the other reduces. So class, I arrange them in order of atomic size, which I taught you. Remember that who has the smallest atomic size is neon, because it has only 2 shells, so it's the smaller size, right? These 3 have the same shells, but who has the smaller size? The person with more number of electrons. The more number of electrons, the more the atom will shrink, right? Thereby reducing the atomic size. So this guy, then this guy has bigger shell, of course, now 4 shells. So class, number of atomic size and ionization energy are always going in opposite direction. So if this is atomic size, this ionization, just use that and get it. Because where do you want to start from now? See all their position, close to them, scatter them, they scatter them. Neon. Potassium. Sodium. Who is increasing down the group? How will you do it? Just use the atomic size. Use the atomic size. Now, electron affinity. We have just electron affinity and electronegativity, and we are done. Electron affinity and electronegativity, and we are. Electron affinity. Electron affinity is the energy change that occurs. Electron affinity. Electron affinity is the energy change that occurs when an electron is added to a neutral gaseous atom. Is the energy change that occurs when an electron is added to a neutral gaseous atom. Is the energy change that occurs when an electron is added to a neutral gaseous atom. Is the energy change that occurs when an electron is added to a what? Neutral gaseous atom. It is called electron affinity because it measures the attraction or affinity of the atom. It is called electron affinity because it measures the attraction or affinity of the atom for the added electron. Note that it has the same trend as ionization energy. It measures the attraction or affinity of an atom for the added electron. It measures the attraction or affinity of the atom for an added electron. It has the same trend as ionization what? Energy. It has the same trend as ionization energy. Let's look at electronegativity. So if it held, the examples that we use for ionization energy can go for electron affinity too, right? Because they have the same trend. Whatever you did to get ionization energy, you can do it for electron affinity. What does that mean? It means electron affinity is also opposite to atomic size, right? Electron affinity is also opposite to atomic. So the smaller the atomic size, the bigger the electron. And the bigger the atomic size, the smaller the electron affinity. Let's go to electronegativity. After electronegativity, there is one more electropositivity. Electronegativity is a measure of the tendency of an atom. Electronegativity is a measure of the tendency of an atom to attract electron to itself. Electronegativity is a measure of the tendency of an atom to attract an electron to itself. Electronegativity is a measure of the tendency of an atom to attract electron to itself. Is a measure of the tendency of an atom to attract electron to itself. When bonded with another atom through a bond. When bonded with another atom through a bond. When bonded with another atom through a what? Bond. When bonded with another atom through a what? Bond. It has the same trend as ionization energy and electron affinity. So that saves us a lot of stress. It has the same trend as what? Ionization energy and what? Electron. That is, it increases across the period and decreases down the group. And it also means that it also increases as atomic size reduces, right? It has opposite trend to what? Atomic size. So the smaller the atomic size, the more the electronegativity. So the same examples we use here can also work for it, right? Last one, and we are done with periodic table. Well done if you stay to the end of this class. Electropositivity. Electropositivity is the measure of the tendency of an atom Electropositivity is a measure of the tendency of an atom to lose electrons when bonded with another atom. The measure of the tendency of an atom to lose electrons when bonded with another atom. Through a bond. Through a what? Bond. Through a what? When bonded with another atom, through a what? Bond. Note, electropositivity has an opposite trend to electronegativity. Electropositivity has an opposite trend to electronegativity. Comes electropositivity decreases across the group. Decreases what? Decreases across the period. Did I say across the group? Sorry. Decreases across the period from left to. Electropositivity decreases across the period from left to, and increases down the group. Increases down the. And does what? Increases down the. What does this mean? Say about electropositivity? It means that electropositivity will be directly proportional to atomic size, right? The bigger the atomic size, the more the electropositivity. So atoms with bigger size are more electropositive. So electropositivity does what? It decreases across the. Increases down the. So if they give you those elements again and their sizes, you will now know what to do, right? The electropositivity and atomic size work hand in. So I hope you do with that what you should. Class, we have come to the end of this series, periodic table and quantum number. Periodic table and what? In our next class, the series will now be on chemical bonding, Lewis structure, resonance structure, canonical forms of compounds, bond order. If you have been doing your past and you say find the bond order of HE, and you wonder how they do it. Some of them I just put the answer, not solve. I say see to be solved in tutorials. So tomorrow is the day we're going to solve it, demystify all concepts under chemical bonding and Lewis structure. So class, see you tomorrow. What time is our class tomorrow? 1:31. This same venue, 1:30. We are almost done with chemistry. If I finish chemical bonding bond order, it will just remain thermodynamics and gas laws, kinetic theory of matter, kinetic theory of gas laws. Then I will now start again. I will now start. See you tomorrow, 1:30. Thank you very much.